Good morning, everyone. Thank you for joining me in this discussion. We are going to talk about the professional engineering language, IEEE 100, which covers the standard terminology in electrical engineering. But please note that today we are not just learning about the definitions. Today we are learning a tool so critical that without it, no system you ever design will survive outside. Now let's move on toward our uh, discussion. In engineering, language is not casual. Language is a design. Language is a contract. Language is a compliance. Language is testing. Language is safety. And language is legal accountability. And if your system description is ambiguous, no matter how brilliant your math, no matter how elegant your coding, no matter how clever your circuit is, your system will fail. Now, let me ask you, how many of you have casually used the word ground in your circuits or projects? Now, let me ask you another question. Does ground always mean the same things in a power system, in a signal processing board, in a communication interference, in a medical device? In reality, ground can mean very different things. Protective earth ground, which is intended to protect human safety. This is one of the meaning. Another one is signal reference ground, which is critical for low noise electronic circuits, or chassis ground, which is bounding metallic frames to reduce electromagnetic interference, or EMI. And if you confuse those grounds, a system will malfunction, a safety hazard will occur, a compliance failure will happen, a contract could be invalidated. We had real-world cases like NASA Mars Climate Orbiter crash. In 1999, NASA lost the Mars Climate Orbiter, a 300 million spacecraft, okay, a $300 million spacecraft, not because of the hardware failure, but because of language and unit definition were misunderstood between two teams. The engineering team designing the thruster software used pound seconds to define the impulse. The navigation team used Newton seconds, which is an SI unit, in their calculations. The teams assumed but did not confirm a shared meaning of force. What was the result? The spacecraft entered the Martian atmosphere at the wrong angle and was lost forever. Boeing 737 MAX is also another uh, example of how important the definition and language is. Again, we have the example of FDA medical devices recall, okay, in 2012 to 2020. We are going to discuss these two cases also in detail later on in our discussion. Now, this is why engineering standard exists. This is why IEEE 100 exists. Today, we are going to learn it, and you are going to start thinking, designing, and writing like professional engineers. Engineers whose systems survive because their language survives. IEEE 100 is not a textbook. It is not a casual glossary. It is a formal, authoritative dictionary for our profession. Its official title is the Authoritative Dictionary of IEEE Standards Terms. It has three strategic roles in your professional engineering life. Definition consistency across system and companies. Imagine you're designing a power inverter and your supplier, your customer, your regulator, and your safety agency all have different understanding of the terms like voltage, ground faults, total harmonic distortion, or rated load. How can you possibly ensure interoperability? You can't unless you all agree to use the same definitions. IEEE 100 ensures that when we say voltage, we all mean exactly the same thing. Another aspect is cross-standard alignment. Modern systems involve multiple standards. For example, IEEE 519 defines harmonic limits for electrical system. IEEE 1547 defines interconnection standards for solar panels. And IEEE 802 Part 3 defines Ethernet networking. Now, all these standards rely on a core definitions, and those definitions referenced in IEEE 100. If you misunderstand a definition at the foundation level, the entire system of standards collapses around you. Another aspect is legal and compliance authority. In legal disputes, safety audits, and product certification, the court, the regulator, and any third-party tester will not accept your personal interpretation of the term. They will accept only IEEE definitions, ISO definitions, or formally cited standard dictionaries. IEEE 100 defines the technical truths in professional and legal spaces. Now, the technical structure of IEEE 100 is as follows. We have organization of the terms. So IEEE 100 organized the terms alphabetically, but internally also it categorizes based on the engineering domain. For example, electronic, communication, control systems, power systems, software, or safety, or even environmental aspects. Each term entry typically consists of the primary term, which is normally is in boldface, as the exact standards label. A definition is short, clear, and unambiguous. Okay, there might be optional notes in some of the terminologies that the purpose of these notes is to clarify the meaning of the definitions for that specific terminology. But how we can read and interpret the IEEE 100 terms, how we can work with this standard. First of all, when you want to use IEEE 100 definitions, you have to identify the domain of the contest, because one specific word could mean different definition, could mean different meaning, okay, to different domain. For example, we talked about the ground, okay, and we see that there are different things, different meaning to like power system, between power system, or signal processing, or communication. When we talk about the power system, we have a different meaning for the ground, and when we talk about the electromagnetic interference, again, we might have a different meaning for the ground. After we identify the domain, now we focus on a formal construction. What that means? That means IEEE 100 definitions are constructed to eliminate vagueness. Okay, so that would require to have a specific, very clear characteristics for each definition. If there is a boundary and condition, they have to be mentioned in the definition. If there is even exclusions, we have to like consider those, and we have to read carefully about those meanings because some of the limitation, some of the descriptions would actually affect significantly about the result of using those terms in your design or in your reports. Okay, the next item is the units. The units are very critical when we're talking about the design project in engineering, and specifically in our discussion, the terminology and the definition of the terminology. Most technical terms are tied normally with a measurable quantity in engineering. Okay? When you talk about a measurable quantity, always you have to ask first question should be, what is the unit? Are we talking about the SI unit or imperial measurement? What is the unit that we use to describe that specific quantity? When we describe all of this, now we have to cross-validate multiple definitions. Okay, one term could appear in multiple disciplines. Okay, cross-validation is to ensure that all those disciplines are talking about the same term, the same meaning. If there is a difference, we have to note that and we have to consider that when we are gonna use that term in our design or in our report. Now, how to apply the IEEE 100 in your writing? First of all, when you want to like apply this standard in your writing or report or the design, okay, what you have to do is at first place identify the technical nouns. Okay, this is the first step. Now, review your document and identify all the nouns that require the precise definition. We are going to have an example later on to kind of like see what we mean by that. Second step is check against IEEE 100. Now you have your nouns, okay? Go through the IEEE 100 and see what is the official description, what is the official definition of those terms are. Verify that in your writing, you actually consider the definitions in IEEE 100 and you are precise, matched with that definition, that standard definition. Third step, defining the missing terms. Now you might have like a terms in that are isn't in IEEE. Okay, you are using a terms that there is no IEEE 100 standard definitions for it. Now, when you read the IEEE definitions, there is a structure for the definition. If you're using a term that you are introducing into the report or the writing and you cannot find a standard definition for it, you need to structure a definition as a note or like a footprint, okay, to describe exactly, very clearly, and with the unit, measurable quantity, all those little kind of like details that you have to mention to have a specific definition for the term you are introducing to your report. Okay, and then at the last step, you validate for compliances. Okay, and ensure that all the definition that you are using, all the term that you are using, okay, is consistent within the IEEE standards. It's more important is the most important aspect of that is to protect yourself actually during a regulatory audit because any vagueness introduced by you means that any hazard, any failure, any kind of like risk that happens because of that vagueness is your responsibility. You didn't define those measures precisely and accurately. So you introduce a vagueness, you are responsible for what happened after that. Now, the critical terms from IEEE 100, let's talk about some example, like voltage. The, the voltage are defined as the difference in electrical potential between 2 points in a system. Okay, let's talk about it a little another time and slowly. The difference in electrical potential between 2 points in a system. Okay, it defines a potential as a potential is the voltage as a potential difference. It's not an energy itself. It's not a single scalar. Okay, it's a potential difference. That means it's a relative value, and meaning that it's a vector parameter, not a scalar parameter. So it has a direction. Okay, so it's potential difference. Explicitly, it referenced the definition reference that we have to have 2 points. Okay, sometimes, yeah, granted, sometimes you talk about the voltage of a single point, but that's not the case. It's not a voltage of single points. Normally, we consider 1 point as zero as reference. Sometimes in power system we call it ground. Some is in sorry in a signal processing we call it ground. Okay, and uh, we consider that as a voltage zero as reference. So when we talk about a single voltage, single point voltage, that in reality we're talking about the voltage as a potential difference between that point and that reference point. Okay. Now, no mention of the flow, current, or power. It's just the potential difference. Are we good? Now, compared to casual misunderstanding, let's talk about the uh, casually talking about the voltage. Voltage is often wrongly described as energy stored or power availability. That is incorrect. For example, when you talk about the batteries, you talk about the voltages, and you consider, and normally it's not engineering kind of like understanding, but a common understanding is that voltage represents the amount of energy, which is not true. Okay, it's just the potential difference between the two ends of that batteries. Just like height, okay, you measure height as a difference between two places. Okay, two places on Earth, like for example. Okay, this is gonna be the same. Now, let's talk about the term that we talked to introduce earlier and we discussed earlier, the ground. Let's see what are the definitions of the ground in IEEE 100. Now, this specific term, the meaning and the definition is different in different categories. Okay, so if we are talking about the signal ground, we are actually referencing to a point for the signal within a circuit. If we're talking about the protective ground, we are actually talking about the connection intended to protect persons for electrical shock by bounding exposed conductive parts to the earth. So simple word of ground could mean different thing. Or classic ground is normally is electrical connection to the metallic frame of the equipment. Okay, when you're talking about designing electronic or like a communication or IT equipment, when you talk about the ground, you are you are talking about that connection that connect the frame of that equipment to the kind of like the uh, electrical connection to the protective ground. Now, let's talk about more kind of like uh, definitions, okay, in the IEEE 100. Okay, some more example of the rise time. Some more example like rise times and frame. When you talk about the rise time, for example, the definition in IEEE 100 is that the time requires for a signal to change from a specific value to a specified high voltage. Now, technical points on this. You must define an initial and final level, e.g., for example, 10% to 90% of the final voltage. Okay. Or the most important kind of like the most famous one is the time constant, the rising time in a time constant of a LC or RC circuit or RL circuit. Okay. When you talk about the time constant, it's not just a raising time. You have to define an initial value and the end value from zero, for example, on time constant to 63% of the final value. That would be the time constant. So initial and end value. Rise times must be measured within the specified system bandwidth. Okay, that's another important of that definition. Now, practical application. Defining the acceptable rise times limits. For example, we might have a design and we wanted to like describe the rise time less than 5 nanoseconds. That's not just that. You have to mention specifically what is the initial value and what is the final value that defines that rise times that should be less than a 5 nanoseconds. Now, we could define it from 10% to 90%. Now we have a proper rise time definitions in our project. Just mentioning less than 5 nanoseconds does not completely covers the aspect of the rise time. And it could be misinterpreted based on the kind of like understanding or like assumptions between different engineers or different teams. Now, another term is frame, like in communications. The IEEE 100 defines frame as a sequence of bits composed of a data and control information that is transmitted as a unit. Okay? This is the exact definition. It clearly specifies frame structure, okay, and specify what it means as a transmitted information. Now, we talked about the problem that ambiguity could introduce into a engineering project. We mentioned NASA Mars Climate Orbiter, okay, when teams use different definition of the impulse unit and the force, navigation software expected Newton seconds, when another one, the thruster control software assumed in the unit as pound seconds, and there was no cross verification of the definition, which ended up in losing over $300 million in less than a minute. So what it tell us? That is story. That story tell us every single terminology, every single term that you use, you have to specify the units for that term clearly. We cannot assume shared understanding without confirmation. Okay? When you talk about the voltage, you assume that everyone knows that the unit is volt. When you talk about the current, you assume that everyone knows that the unit is ampere. But if you wanted to do a professional practice in engineering. When you talk about the voltage or current, although it is very well established terminology, you always have to mention the units. Okay, that's a very critical aspects of writing in engineering kind of like field. Beside that, when you use a definition for terminology, you need to reference to a specific standard. Okay, and you need to explicitly tell if there is a standard that is not implied. So it's a very important thing. So you need to standard, you need to define that, okay, I use this definition based on what standard. And the other engineers, when you talk about this, when you use my writing, this definition would not be consistent or would not be applied to this category of standards, for example. Okay, so these are the most important aspects that we learn from that specific experience, that specific failure that NASA experienced. Now, another incident that happened because of the terminology is the Boeing 737 MAX. A tiny sensor called angle of attack incorrectly triggered in a new stabilization software. The stabilization software is MCAS. You might know, heard about it or worked with it. MCIS engaged based on a single erroneous reading. Sensor documentation across subcontractors was ambiguous. Okay, some considered that as a data refresh rate, okay, that angle. Some considered as error tolerance, and some considered that as a test coverage responsibilities. These ambiguity between these terms resulted in two crashes, which is not about just the financial, like billions of dollars in damage. The most important aspect was that it resulted in more than 340 loss of lives. People died because of that ambiguity. So now, what that teaches? What is the lesson learned from that incident, that unfortunate incident? We have to define sensor behaviors precisely. Mhm. So if we're talking about a single quantifiable parameters, for in this example, the angle of attack, okay, there is gonna be a measurement within our system, the input to the system. We have to define precisely how that measurement works, what is the sensor's behavior, how it would measure and translate that to a signal for the control system, for the processing system. Okay. And after that, we have to document operating condition explicitly because different operating condition could affect the accuracy of the sensors and the operation and efficiency of others electrical circuit and electronic circuit like the processors or the control units or the actuators in that system. Beside that, we need to make sure that the supplier's specification are internationally recognized definitions. When we talk about the global project, international project, okay, we cannot just use our national definitions. Like, for example, our national unit, for example, in the United States, normally we use imperial kind of like units for the weight or uh, length. But the other countries all around the earth use SI unit. So neglecting that fact could be catastrophic. So we need to have, this is just a unit. There are differences in uh, definitions too. Another example, you can talk about, like in power system, you can talk about the harmonics when we talk about the fundamental frequency in the definition of the harmonics. Okay, in United States, that means the value of the 60 hertz component in the spectrum. If you simply consider and say, okay, we are kind of like using fundamental frequency for this purpose, in United States, it means different signal than all around the world. Because their fundamental, like Europe fundamental frequency, Asia fundamental frequency is 50 hertz. Okay, so we need to be precise and exactly mention what we mean. These are the definitions and the importance of those concepts. Another example, we introduced that before, the FDA medical device recalls. It happens between 2012 and 2022. Multiple class 2 equipment were recalled because of the malfunctioning. That was blood glucose monitors, cardiac implants. All the cardiac implant is the kind of like a little kind of like effect, cardiac implants or infusion pumps. All of them were recalled because of the vague terminology. Okay. Example of the failure, safe operating current. That definition left undefined across software and hardware teams. That ambiguity creates problems, like in the blood glucose monitoring, or acceptable thermal rise. It was not quantified in clear standard units, which basically introduce a malfunction in our circuit and in our system. They didn't use a precise references to IEEE or IEC standards or FDA terminology. That means some teams, because some of this terminology that we are talking about that are defined in IEEE 100, in IEC, they might have a slight different in definition, or in FDA terminology, or in BS standard, or in other countries' local standards. Okay, they might have a difference, slight differences between the definitions. If you do not reference precisely which definition you are using, okay, that also could create mistakes or a misunderstanding between two teams that are working with different standard frame. Now, what is the lessons that we learn from that medical device recalls? We learned that, okay, when you talking about the terminology, you always quantify. For example, that safety. You need to quantify the parameters of safety. What safety means, how I can quantify, how I can measure it, how I can control it, how I can correct the malfunctioning or the errors in safety. If you don't quantify that, you can measure it, you can control it, you can optimize it. And every team would try their own kind of like understanding of the safety, meaning it is gonna fail, it will fail. Always specify environmental operating range. That's also a very important thing. I happen to kind of like read a lot of engineering writing. Most of them like the papers that are published. okay, when they have experimental kind of like design, and they did not consider to mention, okay, what was the environmental conditions that they run it, or that's the from the research perspective. From the industrial perspective, ambiguity on the environmental operating range could create a lot of problems. For example, in power system, any junction box that is used to kind of like encapsulate the electrical system, and precisely the one that is used in outdoor, they have to have a IP mark. How effective they are on penetration of the dust and water. If you don't mention that, that means someone is gonna use it in a wrong place. That means that will cause a failure. Now, another thing, always link to authoritative standard. As I mentioned before, one of the problem in that medical device was the slight differences between the IEEE 100 and the IEC standards and the FDA guidance. Those slight differences creates an ambiguity, create a misunderstanding, create a kind of like slight differences between the design, between the teams that working on that project, which ended up in failure. In each case, each of those cases, people trusted informal language. And in each case, people died, system failed, companies collapsed. Now we move to practical skills, how to apply IEEE 100 in your work. Now that you understand why IEEE 100 is mandatory, okay, I wanted to train you how to technically use it as engineers during documentation, design, specification, or compliances work. IEEE 100 is organized, okay, alphabetically. So it requires that 5 steps process when you wanted to use it. We introduced that 5 steps, okay, which was specifying, identifying the technical terms, the nouns, checking against IEEE 100, avoiding vague adjectives like large voltage, high current. These are not precise kind of like definitions. You need to say, okay, what it means when you say high current. Does that means 10 amp or 100 amp or 1,000 amp? Okay, or then specifying the operational domains, because those terminology may have a different meaning between the domains that in IEEE 100 are defined. And at the fifth step, we validate the requirement. We have to have 100% precision. Okay, everything is quantifying. Every unit should be defined. Every definition should be referenced to standards. If there isn't a standards that might be used and that definition would not apply, it should be noted. Okay, so now let's talk about the IEEE structure. As we said, IEEE structure is organized alphabetically. It's not just the alphabetical word list. Each term belongs to one or more engineering domains, depending on how it's used. Okay? Now, Main technical domains in IEEE 100 are electrical engineering. Example are voltage, current, impedance, fault current. So these are the basically the uh, 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 general definitions that applies to everything electrical engineering. Then we have a category of electronic. Now, these category, those definition in electronic would not apply to any other domain, like logic gates, noise margin, band gap voltage. We have communication category, which talk about, like, for example, frame. We already talked about the definition of the frame in previous slides, or the word protocol, or latency, or bandwidth. They are specifically defined for the communication category, and these terminology should not be used kind of like across those domains. Control system has their own category. Software and embedded system has their own category. Power system has their own category. Safety and compliances has their own category, and environmental kind of like concepts has their own also category. So when you look up uh, for a term, you must check which domain is belong. We already talked about the example of ground. Never assume that a one meaning fits all domains. Okay? Now, how to read IEEE 100. Okay? These IEEE 100 are written in formal, compressed style. You must read them precisely. Each word matters. Okay? Like a technical specification document. Okay? We have a primary term, okay, which is the term that we wanted to have a definition for, and is normally in boldface. We have a short, direct statement without any casual language, designed for unambiguous interpretation, with the units, with the quantifying aspect, okay, which is called definition of that primary term. And sometimes we had notes which basically are aimed to have a more clarification, especially when there is a term that is using in different that is being used in different categories or different discipline. We talk about the voltage, okay, and we talk about the uh, 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 definition of the voltage precisely of what we mean by these structure. Now, you must always recognize the domain of a context before applying the term. For example, the term ground. In electrical safety is protective earth, is signal processing is reference node. Frame. In communication means packet data unit. In structural is load-bearing member. Feedback in control system means error correction. In audio means acoustic refeed loops. See how different are the definition of one word in different categories or different discipline. Now, when you write a design document, you have to always identify every technical noun you use. Cross-check if the term is defined in IEEE 100, okay? If it's code, the exact IEEE 100 meaning, uh, if needed, or ensure using matches exactly, okay, without misinterpretation. So when you're using a definition, you need to exactly quote the definition from IEEE 100. Or as we talked about before, if you don't have that definition in the IEEE 100, you need to precisely define that terms for to avoid misinterpretation. Now, let's practice one example. The example is like for example, the voltage specification. Let's analyze the statement that we have here. The device will handle big voltages. Okay, what is the problem with that? What's wrong with that? What's IEEE's treatment? And how would you write it or rewrite it, this specific statement? Now, in IEEE, we know that we have to be precise, measurable, and contextually clear. We have to define, for example, here an exact voltage range. Big is ambiguous. We have to define it an exact voltage range. We have to define a specific measure point. Okay, between the device will handle the specific range of voltage where in the system, between which 2 points. Okay, and in define a condition, in what condition the device has to handle that voltage, that range of the voltage between those specific 2 points, in what condition? Is it a steady state? Is it a transient state? Is it during the fault condition? So you see how these details actually make a extremely different meaning and understanding of this simple uh, statement. Another example, the statement is protect against a strong current. Strong is ambiguous. We have to specify, okay, an exact range for the current. And not just that, what value of the current, like if you're talking about the AC current, okay, we have to talk about that. Okay, what is that range applied to? Is it the peak current? Is it the RMS value? Okay, or is it the fault current? And when we say protect against a strong current, that's when you say protect, what protect? What is the meaning of the protect? What method to protect? Is it going to be a circuit breaker? Is it going to be a fuse? Is it going to be a relay trip mechanism or anything else? Like other examples of protecting a device against a, a specific amount of current. And more than that, we have to reference the IEEE standards that we are going to use for this definition of the current and protection. Okay, so we know specifically what is the protection, what is the quantified parameters of that protection, what is the current, how we measure the current, what is the unit of the current, how we calculate the value of the current, is it a peak or RMS or anything else, what is the state that we calculate that current, and we have to like protect the circuit for that specific range of current. Okay, so is it gonna be and where is that current is measured? Is it the terminal, output terminal? Is it the kind of like current passing through the switches? Is it the input terminal? Where we measure the current? What is the error of our measurement? What is the actually acceptable error of measurement? How this specific measurement could vary and at the same time make sure that we actually protecting the system. See how much details in we need to just for these little terminology. The term says protect against a strong current. How many details we have to add to this specific kind of statement, so we know that there is not ambiguity when we talk about our design. Now, let's have another examples, the different example of bad specifications. Okay, let's talk about them. And we are gonna talk about how we could manage to fix those examples. I want you to see how you could use the IEEE 100 dictionary and their definition to change the ambiguity in a bad specification into a precise and professional statement that could be used between all engineers and avoid misunderstanding. Now, first one, for signal transmission, the statement is the system shall send signals quickly. Now, I will read this statement. I want you to think about that, okay? And in your head or on the paper, try to find the ambiguity in those statements, okay? And we are gonna talk about them in upcoming slides. Another statement is for voltage handling. The statement says it must handle big voltages without breaking. Next one, user safety. It should protect users from electric shocks. For environmental resilience, we had a statement, it should resist temperature changes and work under all environmental conditions. In communication, we have the statement, it must interface with a standard communication device. Now, I want to make a comment. These statements are not just haphazardly put in here. I grabbed these statements from already existing document. So someone make these mistakes, and we are gonna see how we could fix it. Now, example one, the signal transmission. See how vague the statement of the transformation is. He said original statement says you have to send signals quickly. What it means quickly? What is the speed? It's ambiguous in this statement. We didn't define what is the signal type. What kind of signals should be sent or transmit with that specific speed? How we could measure that specific speed and what is the unit of that? And what is the test condition? Under what condition we should be following these conditions? Now, let's refine this statement. We could say the system shall transmit control signals with a raise time not exceeding 5 nanoseconds between logic levels, okay, measured between the transmitter output and the receiver input. See, now we define what is the signal, okay, what parameter we should use to measure the speed, okay, what is the exact meaning of quick, so what is the speed that we have to target, what is the unit of that parameter measurement measured for to identify if we're following the rule or not. and where we make that measurement, from what point to where, from where to where we need to transmit this data with that speed. Now, I wanted to pause and let you think we missed one specific term. There is still one ambiguity in our second definition, and I want you to think about it and see if you can find it. I'm going to pause for a moment, and then I will mention that. Now, look at look at these uh, definition of rise times. It says a rise time not exceeding 5 nanoseconds. We already talked about that. Rise time not exceeding 5 nanosecond. What is the definition of rise time? The definition of rise time needed an initial point and a final point. That 5 nanosecond is measured for what differences? From 10% to 90%, from 0 to 50%, from 0 to 100% of the value. What is that rise time, initial and final point? So see how easy is to miss a point when you're talking about the specification of a terminology. Now, another example, that voltage handling. We had the original phrase was handle big voltages. Does not have a meaning in engineering because its magnitude is ambiguous. The conditions are missed in this statement, and there is no measure point or unit mentioned that. Okay, now how we could do that? We could identify missing parameters. In that phrase, as we said, the first step is to acknowledge the nouns, find the nouns. The noun is the voltage. Okay, so what is the voltage value? What is the measurement point? We have to follow the definition of the voltage in IEEE 100. See, we define that voltage as a potential difference between 2 points. But in this definition, we didn't mention those 2 points. What is the measurement of the 2 points? What is the voltage value? When we say big as an adjective for that noun, what the big means? And all that, what is the operating condition? In what condition we want to have this design? Now, look up the voltage, or like, for example, a steady state in IEEE 100 for precise definition. I want you to look up that by yourself. But now I wanted to like give you an enhanced version of that statement. In enhancement version, we could say the system shall withstand, handle is not a good word, shall withstand, and again, shall is important because it create a mandation. So there is no condition that we could ignore this rule. The system shall withstand, for example, a steady state input voltage, so it between the two terminal of input up to 600 volt RMS. So we define the voltage, we define the quantity, we define the units, and we define what parameter, what kind of voltage we are measuring. Is it peak or RMS? Between, when we say input voltage, is still ambiguous, between line and neutral conductor. And in what condition? Under nominal operation condition. So in fault condition, in transient condition, that specific voltage boundary does not apply. In nominal operation condition, and all these verbs that all these nouns that we use in the enhanced version, which is the steady state, the voltage, the RMS, the line conductor, the neutral conductor, nominal operating condition, all these nouns are defined based on IEEE 100. So if you want to know what those means, go read IEEE 100. And then you could understand exactly what this statement means. Now, try to practice these 10 examples by yourself. I'm gonna pause, and you can also, this is a video, you can pause and try to like correct these statements by yourself. Now, let's go through one by one. The first one was the device shall send signal quickly to control system. Okay, it's a transmission speed. Now, how we could enhance it? We could say the device shall transmit digital control signals with a raise time not exceeding 5 nanoseconds between logic high and logic low. Now, remember, we have a definition for rise time. Logic high, logic low, because it's digital control. There is no 10%, 90%. 0, 1. Logic high, logic low levels should be 5 nanosecond. Measured at the transmitter output. So this speed need to be at transmitter output and the receiver input according to the IEEE 100 definition of the signal and rise time. Now see how specific the next statement is, the enhanced statement is regarding compared to the first statement. Now, there is no way that someone could misinterpret the second enhanced version. The next one, it must handle big voltages, the voltage handling. The system must handle big voltages without breaking. Now, what is the nominal operation? What is the voltage? Where? In what condition? What kind of voltage? Is RMS, peak? What kind of voltage? Now, let's try to enhance this. We could write the system shall be capable of withstanding continuous input voltage up to 600 volt RMS, where between phase and neutral conductor. In what condition? Under nominal conditions. Okay, now, and up to 1.2 kilovolt. Now, peak voltage. The first one was RMS, this one is peak. During the transient overvoltage, as defined in IEEE 100 for voltage and root mean square. Is that clear? See how different it sounds when you precisely address all the ambiguity. Next example. It should protect user from shock if something goes wrong. You know how bad it is. And again, I didn't make these statements. I grabbed them from already existing material. Now, let's define it. Now, we could write all exposed conductive part. Okay, see where these protection apply to. All exposed conductive parts shall be permanently connected to the protective earth conductor. Okay, so this part says how we apply this rule to mitigate the risk of electrical shock consistent with the IEEE 100 definition. So that's another enhancement that we could make for the ambiguous statement. Next one, for the communication requirement. The statement says communication must be fast and use regular devices. You could already see the problems with that statement, how we could enhance it. We could say the system shall implement Ethernet communication compliant with IEEE 820.3, transmitting what? Frames with a minimum data rate of 100 megabit per second using what? Category 5E or higher cabling, okay, consistent with IEEE 100 definition of frame, communication, and protocol. Okay, now think about that and the difference of these two statements, the first one and the enhanced one. Another one, the system shall ground itself properly to avoid problems. How we could enhance it? We could say all system chases and shielding elements shall be bounded to protective earth, okay, not just ground, protective earth, in accordance with IEEE 100 definitions for ground, chases ground, and protective conductor. Grounding resistance between chases and earth shall not exceed 1 ohm under normal condition. Now we define the condition of the grounding, condition of the protection, actually. Next statement, it must detect if the power is not normal and shut down fast. Statement, what is the deviation when we say power is not normal? What is the condition recognition? Is it over voltage? Is it under voltage? What is not normal? Response time, how fast it should shut down. Now, how can we enhance it? We could say the system shall detect under voltage or over voltage conditions when the supply voltage deviates by more than 10% of nominal based on RMS measurement. See how defined is, how the specific is, and shall initiate shutdown procedures within 10 milliseconds of detection. Okay, so a starting point is important according to the IEEE 100 definitions. See how different it sounds and how different it means? Next one. It should run well even when there is noise in the environment. Okay, what means run well? What is the EMC performance? Maintain functionality and communication integrity. What is the noise tolerance? It's not just when there is noise. What is the tolerance? What is the values? Specific quantified parameters. And what is the definitions based on? Now we could enhance that statement by writing the system shall maintain functionality and communication integrity in environments with electromagnetic noise levels up to 10 volt per meter, 10 volt per meter. Okay, I'm insisting because meter is not the unit that normally used in United States. 10 volt per meter radiated electromagnetic fields, confirming to the IEEE 100 definitions. Next, the display should show data clearly no matter what. How we could enhance it? The device graphical display shall maintain a minimum luminance. The minimum luminance, what that means, the data clearly show. No, we have to define the quantifiable parameters. Shall maintain a minimum luminance of 400 CD per square meter under ambient lighting up to 1000 lux and a viewing angle of at least 80 degrees without significant loss of contrast, consistent with IEEE 100 definition. See, that little kind of like a statement. Show data clearly, okay, show data clearly. See how we defined it? Maintain a minimum luminance of that specific value under ambient lighting of that specific value. So the condition is important. How we measure, what is the condition of measurement? Viewing angles of at least 80 degree. And what is the criteria? Without significant loss of contrast. Another one. Battery charging should be safe and fast. What that means. Now, what are the points that we could address in the ambiguity of this statement? Now, the battery charging module shall operate with a charge current not exceeding the manufacturer's rated limit for the battery pack. For charging time, that device shall achieve full charge within a specific time with a specific unit, 2 hours. At what? At a standard condition, which means 225 degrees Celsius, at nominal rated input voltage. So if the input voltage is different, that's not 2 hours. If the temperature of environment is different, not 2 hours. And it should be all those definitions of charge, full charge, nominal rated voltage, charge current, all of them are defined in IEEE 100. Okay, thank you for your attention. Please let me know if you have a question. I will be happy to answer that. And thank you for watching this video. Have a good rest of the day.